Good morning again. We're now going to talk about chapter 1.3, which is about the composition of pure substances. For those of you who don't remember from your previous science courses, so a substance is anything made of atoms. So anything solid, liquid, or gas is called a substance. Now, a pure substance means that in whatever you're observing, there is only one thing. There's only one molecule or one atom in whatever you're observing. So if it's water, it has to be only water. There is nothing else in the water. Uh, Now, pure substances as well as mixtures are characterized by two types of formulas, and you can see them here on the screen. So it's chemical formulas, and then there are empirical formulas. And there's a difference between them. So as you can see here, it says a chemical formula represents all the atoms in the element, while the empirical formula only represents the ratio of these atoms. For example, C2H4 is a chemical formula because it represents every atom that this compound is made of. So you've got two carbons and two hydrogens. However, the lowest possible ratio of these two elements is actually 1 to 2. So we don't do 2 to 4 when we write empirical formulas. We have to put the numbers to their lowest level, right? So we divide this by 2. So basically, the empirical formula of C2H4 is actually CH2 because it represents only the ratio. For H2O2, which is hydrogen peroxide, which is made of two hydrogens and one oxygen, two hydrogens and two oxygen atoms, the chemical formula is H2O2, but the empirical formula is only HO. For some compounds, this is going to be the same thing. So for H2O, both empirical and chemical formulas are H2O because that's the lowest ratio. And of course, you've got some empirical formulas such as NO2 that have two possible compounds. As you can see here, if N and O are one to two, there are two possible chemical formulas for this, which is NO2 and N2O4. This is not always the case, for example, because uh, N3O6 doesn't exist. It's not possible to make that compound. So sometimes actually you can have only one compound from one empirical formula. Sometimes you can have two or even three, but it's not an infinite number. You can't just keep multiplying this by different numbers and get an infinite number of chemical formulas. Now, uh, there are a lot of questions about empirical formulas, but they're all very similar, and I will show you a number of them so you can kind of figure out what's happening in there. So look at this: how to determine a mass percentage composition of something. It's simple. You just always have to go back to moles. So when you're talking about anything, when you're trying to figure out anything related to empirical or chemical formulas, you always just have to remember the moles. The moles never lie, and use proportions if necessary. So they want you here to determine the percentage of of H and O in H2O. So 1 mole of H2O is made of two hydrogens and one oxygen. Hydrogen molar mass is 1. You can check the periodic table for that, but I mean, it's not necessary here. So hydrogen is 1, right? Oxygen is 16, right? So that's why I put above here. I always do that. I put the mass of molar masses above. So H2O is made of two hydrogens and one oxygen. Actually, it's made of 2 moles of hydrogen atoms and 1 mole of oxygen atom. Remember, moles and molecules are proportional, so you can always just put this 2 in front here and put this imaginary 1 in front here and get this. So now you multiply that by molar mass, and you'll get that the mass of hydrogen in 1 mole of water is 2 grams, and the mass of oxygen in 1 mole of water is 16 grams. Just again, multiply by molar masses. And then what you get is in total, there are 18 grams of water here. Now, all you have to do is simply calculate the percentage. So divide 2 by 18, multiply by 100, and you got 11.1% of hydrogen here. And in the same way, you got 88.9% of oxygen in water by mass. This can get a bit complicated if you got something like this, for example. So this is the same thing, it's just a more complicated compound. So you got here two C's, six H's, and one O, but it's basically just done in the same way by using molar masses. So you can just figure this out and ask me questions if you have them. Now, this is a probably the most common question in AP chemistry about related to empirical formulas. So they can give you something like this: a compound contains only carbon, hydrogen, and oxygen, and they give you the percentages. So oxygen is 48.62. Actually, sorry, carbon is 48.64%, uh, and hydrogen is 8.16%. And the rest is oxygen. They didn't give you oxygen, but it has to add up to 100. So you can just use these two and calculate that this is 43.2. So how do you do this? Well, you can just imagine they gave you 100 grams of substance. So out of that 100 grams, 48.64 will be carbon, 8.16 will be hydrogen, and 43.2 will be oxygen. So you do this in three steps. There's always these three steps. So firstly, you have to determine the number of moles. And you do that by dividing these numbers with the molar mass of carbon, hydrogen, and oxygen. Again, you imagine then that this is a mass, and you just divide it by molar mass, and you get the number of moles, right? So divide mass with molar mass, you get number of moles 4. Divide this, get 8.16, then you get 2.7. These are weird numbers, right? So how do we deal with them? Step 2, we divide each of these three numbers with the lowest of them. So the lowest of them here is 2.7. So you divide 405 with 2.7, divide this with 2.7, this, and you get 1.5 to 3.02 to 1. So this is already a ratio of molar ratio of these elements in there. But we can't work with fractions here. So we simply have to make this not a fraction, and we can do this by multiplying everything by with 2, right? If you multiply everything by 2, get 3 to 6 to 2. So your empirical formula is going to be C3H6O2. So again, your goal is to determine here the number of moles, and you do that by dividing mass with molar mass. Mass divided by molar mass is the number of moles. You can also do the proportion. I just did it more quickly in here. And now let's look at other examples. They could give you this. So look at this. Now they gave you the mass. They did not give you percentage now, but it works the same, guys. So all you have to do is divide all these with the molar mass of these elements, and you get the molar ratio. And let's just take a look at this. So divided everything by molar mass, you got number of moles, right? And then step 2, divide everything by the smallest number. And there is no need for step 3 here because you already know that this is 2 to 12 to 1. And then your empirical formula is N2H12O, right? You might, this is another type, fairly common. So the first one is the most common, then the second one less, and this one is even less common. Say a compound contains only sulfur and nitrogen, uh, and it is 69.6% sulfur by mass. And they gave you the molar mass. So now they want an empirical formula, but they also want the molecular formula. And how do you do this? Again, first you determine the empirical formula by doing the same things, so dividing this with the molar mass of sulfur, dividing this by the molar mass of nitrogen. You can see I use grams here because again, this is the same. If they give you a percentage, you just assume The whole thing is 100, and I got this many grams of sulfur and this many grams of nitrogen. Don't need to use percentages. So, and we do the second step. When you get this, this just doesn't mean anything. So these small differences, you might even get 2.185 here, and you will still consider this to be the same number. If it's close enough like this, then you just consider it to be the same number. So you get this 1 to 1, basically. So you know your empirical formula is Sn. So that's the first part of the question you answered. Your empirical formula is Sn. However, it's also asking you for a molecular formula, but it's giving you the molar mass of the entire thing. So the molar mass of this, just this, would be 46. But I need a chemical formula for molar mass 184. So all I need to do is divide 184 by 46. So it's 4 times bigger. So the whole thing, I just need to multiply both of these with 4, and I'll get my molecular formula. So this is the empirical formula, but this is a molecular formula that has this molar mass. Uh, this is another version of basically the same question. This just is meant to confuse you. So look, let's take a look. So you got a binary compound, two binary compounds of mercury and oxygen, and you heat them up, and then oxygen goes away, right? What does this mean? If oxygen goes away, the mass that remains is only mercury, right? So then you can easily figure out how many grams of mercury you've got, how many grams of oxygen you've got, and then use the same method to derive the empirical formula of each of these two compounds. So let's take a look of the an example. So heating 0.6498 of one of the compounds leaves a residue of 0.6018. So let's say this is the first compound. So the residue means what is left after heating. So what is left after heating, according to what they say here, is just pure mercury. So pure mercury in the first is this mass, and then the whole thing, because they gave you the whole compound, minus whatever is left is just oxygen, right? So you've got this much mercury and this much oxygen, and then you just use the same method, divide by molar mass, and already here you get that you've got 0.003 to 0.003. So that's just 1 to 1, right? So that's just HGO. I don't even need the second step here because I just can see that these two are 1 to 1, right? Uh, the second one is heating 0.4172 grams of the other one results in a mass loss of this much. So that's oxygen. The question tells you again that oxygen leaves. So oxygen is just this. See? Whatever is the difference between the beginning and leaving this much of oxygen. So this minus this, that's just mercury. So that's the residue, right? And again, the same thing. Divide this by molar mass and this, and you get 0.002 to 0.001. And I can already see this is just 2 to 1. So the empirical formulas are these two. This is kind of the most difficult thing they can give you from this chapter. This is another type of the question. Again, this is just meant to confuse you. So let's take a look. A student has equal masses of two pure compounds, XbRO7 and YbRO7. I know where this R is capital. That's weird. So the student heats the samples to remove the oxygen, right? And the oxygen goes away. He lets the ample. It's just a. They're trying to explain to wherever you keep the sample. The sample. They want to say the sample probably. Uh, Although there is a kind of a glassware that has a similar name. So, anyways, it cools down, and you measure the solid residue, and which information can the student derive from this process? Can you determine boiling points like this? So you just heated something and you measure the whatever is left. And whatever is left is basically just going to be XBR and YBR because oxygen is just going to go away. That's what the question says. So you're not determining boiling points, right? Densities, densities, gram per volume. You don't even know the volume. It's very confusing to even think about it. Oxidative ability. Oxidative ability is something that didn't even happen here. So it has nothing to do with this. It's just there to confuse you. Molar masses of X and Y. You can. So this is basically just doing that. It's just doing that. So if you can measure the molar, if you can measure the mass, you can easily determine the molar masses of X and Y simply through basically reversing kind of this method. And let's see if I'm right. Yeah, yeah. So again, this is the only answer that makes sense. Sometimes you're going to have to kind of make educated guesses here, just so you don't have to spend too many minutes on one question because you basically